By this time, we're comfortable thinking about all of the motions that a molecule can undergo, translations, rotations, and vibrations. But if we zoom in and look at the motion of a molecule, we realize that they're undergoing all of these motions all at the same time. However, we tend to treat them as separate motions of the molecule. So why is it that we can treat degrees of freedom separately? Let's look at the energies required to excite each of these different motions. This is most easily done by looking at an energy level diagram such as the one shown here. Let's start at the left-hand side of this diagram with electronic motion. Here we can see the highest occupied electronic state, or the ground state, and the first excited state. So if we were to try to excite an electron in this molecule, we would have to put in the amount of energy that matches the energy gap between the ground state and the first excited state. This is quite a large amount of energy and corresponds to typically ultraviolet or visible photons. On the other hand, to excite vibrational motion, to get the molecule to vibrate at a higher amplitude, we don't need to put in nearly as much energy. The energy required to go from the lowest vibrational state to the next highest vibrational state is clearly much less than the amount of energy required to excite electronic motion. This energy is typically in the IR region, corresponds to an IR photon. The energy required to cause the molecule to rotate faster is even smaller and is depicted by the difference between different J levels or rotational levels. This difference in energy is, again, smaller than the vibrational energy required and is in the microwave region of the spectrum. So it requires a microwave photon to cause a molecule to rotate more quickly. As we have discussed, translational energies are so closely spaced that we consider them a continuum. And so we've shown here the translational energies as simply a shaded block of energy levels. They're so closely spaced that we can't see the difference between them. The difference between energy levels for translations is in the thermal energy range. So one of the reasons that these motions are separable is that the energy required to excite each motion are of very, very different magnitudes. And so, if I have only thermal energy available, I don't have enough energy to cause rotations, and so I will excite translations. If I have microwave energies, I can excite both rotations and translations, but I will not have enough energy to make the molecule vibrate at a higher amplitude. If I have energies that correspond to the IR region of the spectrum, then I will have enough energy to cause the molecule to vibrate at a higher amplitude. I may also cause it to rotate more quickly and to translate faster, have a higher velocity. But I will not have enough energy to cause the molecule to be excited electronically. In other words, I can't move the electrons further away from the nuclei and up to the excited state. Although each of these motions is happening simultaneously, I can describe the overall motion of the molecule as a sum of each of these motions. In addition, I can describe the overall energy of the molecule as the energy in translations, the energy in rotations, the energy in vibrations, and the electronic energy. So the total energy of a single molecule is the sum of the energy in each of the motions.